Hey guys, it's Mr. Schwannekamp. Today we are talking about related rates. In calculus, probably the number one type of story problem that you've heard before. All right, so these are the types of problems that are like, as train A leaves the station this direction, train B leaves the train in this direction, those types of questions. All right, this is kind of the sum of everything we've learned up to this point in calculus. Related rates is about understanding how if one thing changes, how it affects the other thing changing. So as one thing changes, so does the other, and understanding that relationship between the two. Hence the name related rates, two things being related. All right. Lots of different things going on. There's lots of different types of these problems, but all of them kind of fold back into the same idea. If you have trouble with this, there's lots of resources online, whether it's other YouTube videos or Khan Academy or anything like that. Just kind of pick what you need and work through it. We'll see how we do. Let's get to it. So, as I said, all of these things kind of relate back to the same concept. So don't get too flustered when things start looking a little bit weird. All right. So applications of derivatives. That's what we're doing. We're applying this concept that we're very confident in now, which is taking the derivative of something. What we're doing is we're analyzing a little bit of motion, or better words, analyzing how the rate of change of one quantity depends on another, hence again the name related rates. The rate of change of a quantity is its derivative with respect to time. So we did implicit earlier in this chapter, but here we're thinking about the change in something. I don't care what that variable is. Maybe it's A, B, X, Y, G. I don't care. But it's the derivative with respect to time. So how are we going to find dy over dt instead of dy over dx? It's exactly the same. So earlier in the chapter, again, when we took the derivative of y, the derivative of y is something with dy dt tagged onto it. Same thing is going to be true here. So keep that in mind. So let's talk about the process for finding related rates. Okay, related rate problems. The first thing we're going to do is we're going to identify all the quantities given in the problem. So we're going to read through the story problem and make sure we understand what is what. Identifying and labeling stuff is going to be really important, especially labeling rates as d what over dt. Okay, so like the change in x over time or the change in y over time, and that will make more sense here in a minute. And we need to consider their signs. For example, if something is growing, the rate is going to be positive, but if something is getting smaller, that rate needs to be negative. So pay attention to that part. Determine which quantities never change. Because if something doesn't change, that will be a constant. And that's a big part of all of this. We're talking about related rates. So if something doesn't change, then we want to make sure we treat that a little bit differently. Once we've done that, we're going to find an equation that relates all the different variables. So whatever equation kind of relates what we need, we're going to find that next. And we're going to plug in our constants. So before we take a derivative, we're going to plug in constants, because if it's constant, it's not going to have a derivative, because a derivative is all about change. So if it doesn't have a change, then it doesn't have a derivative. We're going to differentiate that equation with respect to time. So we're going to talk through all of that, and then finally we're going to plug in and solve. That's going to be our different steps, understanding what's going with what, but that's the idea. And if that doesn't make a ton of sense, it shouldn't. We haven't done the problem yet. All right, so let's look at this. The length of a rectangle is decreasing. So the length of a rectangle is decreasing at a rate of 2 centimeters per second, while the width is increasing at 2 centimeters per second. Increasing at 2 centimeters per second. Wrong emphasis. When the length is 12 centimeters and the width is 5 centimeters, we're going to find the rate of change of the area of the rectangle. Okay, so when in doubt, I'm going to try to draw a picture. So I got a picture here. It's a rectangle. I've got a length and a width Doesn't really matter which one we call what. All right, eventually we're trying to find the rate of change of the rectangle. So we're going to have some area stuff going on here. All right, so let's talk about it. The length is 12 centimeters, so L equals 12. The width is 5 centimeters, so W equals 5. But then we got this. The length of the rectangle is decreasing at a rate of 2 centimeters per second. So if you are decreasing at a rate of 2 centimeters per second, that is the change in L over time is 2. And we could put the unit centimeters per second. But it's not just 2 because it's decreasing. And because it's decreasing, we're going to be negative 2 because it's going to be get smaller and smaller. We also have this, the width is increasing. So the change in width over time is also 2, but this time it's positive because it's increasing. Know what we're ultimately trying to find here. We're trying to find the rate of change of the area of the rectangle. Or in other words, our mystery thing that we're trying to find here is the change in area over time. There's our setup. So now we need an equation that talks about a rectangle that somehow relates length, width, and area. Okay, so we're going to think of an equation that relates all those things together. The equation is going to be area equals length times width. That's my equation. Before we take the derivative, we're going to think, are any of these things not changing? Well, the width is growing, so it's getting bigger and bigger and bigger. The length is shrinking. It's getting smaller and smaller and smaller. I don't know how to draw smaller and smaller and smaller, but you get the idea. Okay, and with that, we're going to decide how is the area changing. And so the width is changing, the length is changing, the area is changing, everything is changing. And so we can go ahead and take the derivative. If something wasn't changing, we would plug it in first. We'd plug in constants. But we're going to take the derivative. The derivative of A is dA over dt. On the other side, we're taking the derivative of two things being multiplied together. So to do that, we need product rule. So first times the derivative of the second plus the second times the derivative of the first. That's my equation. Then we're going to plug in what we know. I'm trying to find dA dt. That's my goal. My length, that's 12. My change in width, that's 2. My W is 5, and my change in length over time is negative 2. We just multiply this all together. 12 times 2 is 24, minus 10. The change in area over time is going to be 14, and that my units are going to be centimeters per second, centimeters squared per second, because it is area. Okay, and we could have figured this out because length was measured in centimeters and the change in width was centimeters per second. So when I multiply those together, that's where I'm getting centimeters squared per second. But it's also the change in area, and area is in centimeters squared. All right, so again, know what we did. We labeled stuff first. This was the most important part, this part over here where we labeled, we drew a picture. We found an equation. If we had constants, we'd plug them in. We didn't. So then we took the derivative, and then we plugged in and solved. That is how we do it. It is not as complicated as it seems. Okay, at first glance, these are tough questions, but they're not that bad. Here's another question that's incredibly common. A 5-meter ladder leans against a wall. Okay, so here's my ladder. It's 5 meters long. The bottom of the ladder slides away from the wall at a rate of 0.8 meters per second. Find the velocity of the top of the ladder when the ladder is 2.3 meters from the bottom of the wall. So imagine what this is. Again, you've got this ladder leaning up against the wall right here. Oh yeah, it's a beautiful ladder. This is going this way. Okay, so the bottom of the ladder starts sliding. We're trying to figure out how fast is the person on top of that ladder going to hit the ground. Okay, how fast are they going to be traveling? That's what we're trying to find here. It's a little bit strange. If we were in class, I'd be able to draw it out for you, or mime it out for you. I don't know. Demonstrate it is probably the better answer, but that's the idea. All right, let's do it. So we're going to identify some stuff. 5-meter ladder. So my ladder, let's draw it over by this picture, I guess, since I got it. Ladder equals 5. That's, boom, done. The bottom of the ladder slides away at a rate. That's a rate. They labeled this as x, so I'm going to call the change in x over time equals 0.8. Is it going to be positive or negative? It should be positive because that's getting bigger. It's the change in x over time. It's a rate. We are trying to find the velocity of the top of the ladder. Well, that's the top of the ladder. So if I'm looking for the velocity of that, I'm looking for the change in height over time. That is my mystery number. When the ladder is 2.3 meters from the bottom of the wall. So that is referring to x down here. X is going to be equal to 2.3 when this is 2.3 meters away from that. They should say when the bottom of the ladder is 2.3 meters away from the bottom of the wall, but we'll assume that that's x. Cool? There's my setup. Knowing this right now, what is going to be true about d of h over d of t? Is it going to be positive or is it going to be negative? Hopefully you recognize it's going to be negative because it's getting closer and closer to, or it's falling down. That side over there, height, is getting smaller and smaller. So if it's getting smaller, it's decreasing, it's negative. So I need to come up with an equation that relates L, H, and W all together here. I'm sorry, L, H, and X. I can't even read my own handwriting. L, H, and X. It's a right triangle. We're talking about sides of a right triangle. So in your brain, hopefully an alarm went off and you said, oh, it's Pythagorean theorem. That is my equation. Okay, it's going to relate the three sides of a right triangle. And we know it's a right triangle because it's the base of a wall. Cool. Once we've done that, we need to decide, is anything constant? Is anything not changing? Well, the x is changing. The h is changing. Is the length of the ladder going to change? And the answer should be no. So before I take a derivative, I'm going to plug in any constant. So I'm going to go ahead and plug in 5 there. So I'm just going to make that 25. All right. And that's really important. Otherwise, you're going to have some messed up things going on here. Now we're going to take the derivative. So we found in the equation, we plugged in constants. Now we're going to take the derivative. The derivative of x squared is 2x dx dt. Okay, we're taking the derivative with respect to time, not with respect to x. So we need to include that dx dt. And then 2h dh over dt. It's the change in height over time. And then I'm taking the derivative of 25. This is the mistake I always make because I just forget it. Okay, the derivative, there's so many other things going on. I forget this easy part. The derivative of 25 is going to get me 0. Great. Now that we've done that, we're going to go ahead and plug in. So I've got 2 times x dx dt. Oh, I know what dx dt is. It is also 0.8 plus 2h. So 2 times h. I don't know h. Oh no, I don't know dh dt either. I've got 2 missing things. So if I got 2 missing things, I'm kind of in some trouble here. I need to be able to find it. And the way I can find that, I got to think of a way that, hey, I don't know h, but I know L, I know x. How could I find that missing thing? Hopefully you're thinking, oh, I could have just plugged into Pythagorean theorem. All right, I know this is 2.3 squared plus h squared equals 25. Let me break out my calculator. So we're just solving. We need h because I can't have 2 missing things over here in this equation. So I got to do a little bit of work here. Sorry, should have had this loaded already, but you know me. All right, so in my calculator, I'm going to take 25 minus 2.3 squared and then square root that. I get 4.44. We want to go 3 decimals that way. It's 2.440, right? Yep, 2.440. All right, so I know what dh dt, or I know what h is. Now I'm trying to solve for this mystery number because that's what I'm looking for, and I know that answer is going to be negative. And so all I'm going to do is I'm going to subtract this to the other side. So I'm going to get negative 2 times 2.3 times, is that 0.8? 0.8, type that whole thing in. So this is negative 3.68, sorry, negative 3.68, and then 2 times 2.440 times dh dt. So now I'm just going to divide by 4.88. So I'm going to take that and divide it by 4.88. Negative 0.754. So the change in height over time is negative 0.754. And that is going to be in meters per second. We knew it was going to be negative because of the fact that it was decreasing. Okay, because that thing was getting smaller and smaller. That is the setup with that equation, though. Hopefully that makes sense to you. It's an important question because we're going to see it quite a bit. All right, I'm not going to go forever with this first video because I think at times we'll get a little bit brain run out. I'm going to do 2 more here, and then I'll cut it in half. That way you can look at the second half. The second half is a little bit harder one. These are the basic ones to start. Water pours into a fish tank at a rate of 0.3 meters cubed per minute. How fast is the water level rising in the base of the tank if the rectangle is dimensions 2 by 3? All right, so you have a square. So look at this. We got this rectangular prism fish tank. The base is 2 and 3. The water level is going up because we're adding water to this thing. So let's label some stuff. Water pours into the fish tank at a rate of 0.3 meters cubed per minute. So this is normally the thing that students struggle with labeling. We're pouring this water into the tank. It's a rate. But what is it a rate of? Look at those units. It is the change in volume over time. And it makes sense. We're just adding more and more water. Oh, that is the change in volume. It is growing. That's how we know it's positive, because we're adding water to the tank. How fast is the water level rising? All right, so they call this H. I agree with them. So our goal here is how fast is it rising? So I'm looking for dH over dt. And that is my mystery number if the base is 2 and 3. All right, so let's see what we need. They didn't give us a whole lot. We got a little bit. I need an equation that somehow relates the base, the width, and the height of a rectangle, and we want to talk about volume. Hopefully you recognize as volume equals length times width times height. That's my equation. It's going to relate those things together. First thing I need to do is identify anything that's constant. Is there anything that's not changing? Hopefully you recognize that that 2 and that 3 of the base is not changing because it is a fish tank. You can't make those fish tanks grow while there's water in them. That doesn't make any sense. So those things are the same. That's my equation. The volume is changing because I'm adding water. The height is changing because the water's going up. Once we've found that, then we're going to take the derivative. So we're taking the derivative of volume, which would be dV over dt. This could have been a pretty ugly equation that we would have had to take the derivative of, length times width times height. But because there were 2 constants, we don't have to mess with that. What's the derivative of 6h? Well, the derivative of 6h is 6 dH over dt. So that's a pretty simple equation. Once we've found that, we're going to plug in what we know, which is 0.3. Yeah, I do that all the time. So in my calculator, all I need to do is take 0.3 divided by 6, and I get 0.05. 0.05, that is the change in height, and so that is going to be meters per minute. Sometimes it's beneficial to keep the units and do some stoichiometry and try to figure out what's going on in the end. Other times when it's the change in height, it's meters per minute, and I don't always try to overthink it if I don't have to. Let's do one more on this video, and then I'll split it in half here because I know we will get a little bit run down. Helium is pumped into a spherical balloon at a rate of 3 pi feet cubed per minute. At what rate is the radius increasing when the radius is 3 feet? Sometimes they give you an equation. Sometimes they don't. I would say you need to know the basic equations like area of a square, Pythagorean theorem, area of a rectangle, volume of a rectangle and a cube, circumference, area of a circle. But if they do a little bit more than that, they will normally give you the equation. This is kind of right on the line where I could see them giving you volume of a cube or volume of a circle, whatever, volume of a ball or not, sphere. There we go. Helium is pumped into a spherical balloon at this rate. And so helium is pumped in. I'm going to draw a picture. Oh, yeah. You're jealous of my amazing balloon skills. There's my balloon. I'm taking helium and I am pumping it in. That's such a bad thing. All right. So we're pumping in the helium. That is the change in volume over time because I'm adding an amount to something here. It's changing the volume. So dV dt is going to be 3 pi. That is going to be positive because I'm increasing. At what rate is the radius increasing? So I want to know at what rate dr over dt, the change in radius over time, when the radius is 3 feet. That's what I know. So they gave me, I want an equation that relates volume and radius of a sphere. They gave it to me. Volume equals 4/3 pi r cubed. Is volume changing? Yes. Is the radius changing? Yes, the balloon is expanding. Pi doesn't change, it's constant. All right, so everything is changing. So we don't have to plug in any constants first. We're going to take the derivative. So the derivative of volume is dV dt. 4/3 pi, that's just a constant, so it's going to hang out. And then I'm going to multiply by the derivative of r cubed. So the derivative of r cubed is 3r squared. Do not forget the dr over dt. Great. Now that we've done that, I'm going to simplify here a little bit. I've got this 3 and this 3, and so those two 3's, I could cancel them out just to make my problem a little bit easier. So the change in volume over time is 4 pi r squared dr over dt. I'm going to plug in what I know. So 4 pi, my radius is 3, so 9. dV dt is 3 pi. I'm trying to find dr dt. So 3 pi equals 36 pi dr dt. Divide by 36 pi, divide by 36 pi. Yep, that should be a 6 in there. You get the idea. 36 pi. And I divide that, I get 1/12 is equal to 1/12. That would be feet per time unit. What's my time unit again? Feet per minute. That is the change in radius over time. Again, we identified our equation. We identified the things that we had to plug in. We took the derivative. We plugged in and solved. These were the basic rates of change problem. Right now, you should feel pretty confident that you could do it. And then we're going to jump into tomorrow, and it will get a little bit tougher. So just be with what you need. Okay, jump on to Khan Academy if you need a little more practice with it. I'll put some links in the notes here as well, so you can do that. And we'll jump into this more tomorrow. Hope that helps.